As I said, the simply supported beam is an example that you see in the aircraft itself. If you treat the whole wing, we can actually think of, even though the wing tips are actually free, because it's two cantilevers attached to each other at the root, it behaves in terms of the kind of deflections it undergoes, like the symmetry in terms of the loading for most phases of the flight, except when the ailerons are deployed, will show that you can rather consider this as the entire wing with at the center. It's essentially almost behaving like a fixed kind of a system. So in other words, whatever is the deflection that the simply supported beam undertakes, you take that as the origin, and essentially you're thinking of this as a moving system where it is kind of mounted onto this, and therefore many of the results of simply supported beams and or cantilever beams you can interchange by just appropriately using double the length for the simply supported beam as opposed to the cantilever, and converting either the tip or the center to each other, and that way this essentially the center of the simply supported beam becomes the fixed end of the cantilever. So that can be done. So many of these have practical implications in terms of aerospace applications, which is what I want to bring to mind, because many times when we study these kinds of simplified models, the tendency is to just say that it's only of academic use and it's not of actual practical use, but it's not so. There can be a lot of direct practical implications of this as well, which is why this is important. And of course, simply supported beams by itself is present in many other examples as well. The other thing is in terms of the fuselage. If you can think of the fuselage as being carried by two lifting surfaces. Essentially your wing is carrying it at one location. If this is the fuselage, the wing is attached at the front and the tail is, the horizontal tail is at the back. So both of them are like kind of carrying this fuselage and flying with it. So in that sense you can think of the wing and the tail as kind of these hinges that are essentially there. One on in the front, let's say this is the wing essentially, and this support is the tail, and this is your fuselage. But then for that case there has to be an overhang, because there's a part of the wing, part of the fuselage which is ahead of the wing as well, right, up to the nose. And similarly, there could be a short overhang over here also from the aerodynamic center of the horizontal tail, a small portion up to the tip of the tail boom, right? So, I'm every now and then bringing in this correlation with aerospace and aerospace vehicles, because you can see where it all fits into in the bigger picture, okay? But coming back, we want to focus on how to solve a simple problem associated with these kind of boundary conditions. Now you see in terms of the conditions, the boundary conditions, things have changed, okay? So over here you know that this particular point cannot move because it is attached and it's also hinged, but it can rotate. Because it is cannot have translations, therefore your u and v are 0. And because we are considering only in the plane of this screen, W would be out of the screen anyway in a 2D motion that is not there, so explicitly it's not mentioned. Even this u equal to 0 is of importance only when you're considering axial loads. Here we are not considering axial loads, we are considering only bending loads. So what is only of importance to us here in terms of the geometric boundary conditions or Dirichlet boundary conditions as we call it, is that v equal to 0. The other condition here now, unlike in the fixed end where both were Dirichlet conditions, both were geometric conditions, one was displacement equal to 0, other was slope equal to 0. Instead, in lieu of the slope equal to 0, we now have moment equal to 0, because this is a pin, it's a hinge. So it is free to move around that, so there cannot be a moment there unless you have an external moment which is applied, but essentially there is no reaction that this can offer as a moment, which is what that is indicating over there, okay? So on this end over here, the last two are exactly the same, whether you have just a hinge or a hinge on rollers. V equal to 0, M equal to 0 are common to both. The only difference is going to come when you have an axial load as well, which we are not considering, where if it's only a pin, then it is U equal to 0. And if it's a pin on rollers, then F equal to 0, because it's free to move around, right? So there's nothing which is restricting it, because we consider this to be frictionless, and it's essentially free to extend as much as it wants or contract as much as it wants, depending upon the load that you apply over there, right? But forget the first boundary condition for now. Focus on the last two on either end, and that's what we are going to utilize in this particular example. So now, unlike in the cantilever problem, where we had the convenience of at least one end having both geometric boundary conditions, that is displacement and slope is given to us, therefore we were able to march on up to the next concentrated load, and from there we got the displacement and slope at that point, then we were able to march on further. That we cannot do here, because V equal to 0 is useful, but we don't have any information on theta. Theta is an unknown. We at this tip we have to determine it. All the information that we have is m equal to 0. So this is an example which is in that sense a little more complicated to deal with than a cantilever, that you cannot use direct integration marching from one end to the other. You have to use definite integral, but you have to use an indefinite integral over here, which will give you integration constants, and then you have to solve for them at the end. Okay. So because the slope is unknown at either end, so it's not that I can't march from this end, so maybe I can march from this end, but here also it's the same situation, right? So V equal to 0, m equal to 0 is this boundary condition at both ends. So which means that I cannot march from the right end either, right? So only displacement and moments are known, so we cannot initiate a definite integration at either of these ends, which means that we have to resort to indefinite integration. It's not a whole different thing or much more complicated, just that we are not able to solve equations as soon as we formulate them. We have to wait for a series of equations and solve all of them simultaneously, because it will be, the solutions will continue to be remaining in terms of certain unknown quantities, which are the integration constants. Okay. So, so we have to eventually go to the final end and then use these conditions as well. If we start from this end, we have to keep on marching up to each concentrated load and eventually reach there, and then using this eventually we'll be able to solve for the remaining undetermined constants of integration. Okay. So the summary of all that is that you're not solving single equations, but now you're solving simultaneous equations, a set of coupled equations for a set of unknown integration constants. And how do we go about doing that? We have, of course, the boundary conditions at both the ends, displacement and the moment boundary conditions, and wherever concentrated loads are applied, there you will also have interface continuity conditions, right? So for example, if there's a force acting here or a moment acting somewhere, then up to that point we can integrate in terms of integration constants we can determine, and then from there we have to go to a new place, as new integration constants will be there, and etc. And also in terms of the reactions, in this case it's a statically determinate problem, so you would have already got all the reactions, but in a statically indeterminate problem, along with integration constants, you will also have other unknowns, which are the yet to be determined reactions, because not all reactions have been determined using static equilibrium. Here it is a statically determinate problem, we don't have that issue, but nonetheless we have all these integration constants still floating around, which means that you have to use these two sets of equations simultaneously in order to solve for all the integration constants at one shot, rather than in a series, in a step-by-step fashion. But the end of the story is that you have a certain number of unknowns, you have a certain number of equations, and these two numbers are equal to each other, always for simply supported beams, always for all statically determinate problems. What happens with statically indeterminate problems, we'll see shortly. Okay. So the reason why you have these number of equations equal to each other is an exemplification of the fact that it is statically determinate, but we will see that when we go to statically indeterminate problems, the number of unknowns will be larger than the number of equations. But once we invoke the deformations as well, we will have additional equations, and once you add those number of equations, still this statement that number of unknowns equal to number of equations will still be valid. It's only from looking purely from the point of view of equilibrium that we will find that this is valid only for statically determinate, that these two are equal. But for statically indeterminate, the number of unknowns is greater than the number of equilibrium equations, but not all the equations. Okay. Now, as I said, one of the things to determine is the integration constants. The other to determine is the reactions at the ends, right? So, if it is a free beam, then you do not have any reactions at the ends. Like if you consider the whole wing as one single beam, then what is happening is that these two ends are free ends, which means that there are no reactions there. There is no support at all. How can you get reactions? There is neither a fixed support nor a hinge support or a hinge on roller support. Nothing is there, right? So, which means that you do not have constraints. But more often than not, you will have such constraining surfaces. For example, if you are constraining half the wing, then the way the wing is attached to the fuselage, that attachment many a times can be a good enough approximation for that is a fixed end. So therefore, which is why we can treat this as a cantilever. So then if it's a fixed end, then the force that the fuselage exerts on the wing, as well as the moment that the fuselage exerts on the wing, neither of them are known, and those have to be determined, which is the purpose of this slide, that we are talking about constraints, especially the reactions coming up there, and therefore certain constraint forces and moments that are there. Okay. In a fixed end like this, both force and moment will be unknown reactions. In the case of a hinge, for example, the moment is known to be 0. It's only the force which will be an unknown to be determined. Okay. So we will see how those things are determined. The beams, currently we are looking only at all deformations being on the plane of this screen, which means it's a two-dimensional deformation. We are not allowing it to come out of this, whereas in reality it can come out, but that extension, as I said, we will do shortly. Okay, but right now focusing on 2D deformation, obviously within the plane, every point can have 2 translations and 1 rotation. That's all that is possible, but now we are not focusing on points, we are essentially looking at cross sections, okay, and those cross sections are shrunk to a point on the reference line. So the reference line, or even a curved beam, a reference curve, is essentially made by shrinking all of the properties of the cross section to a point, which is the centroid, area centroid of that particular cross section. It is shrunk to that, and all the mass distribution effects and all other effects, the geometric distribution effects, everything is essentially getting shrunk to that. Right now we are focusing only on statics and not dynamics, so the mass doesn't play a role over here, the inertia doesn't play a role over here, but the moments of areas do play a role, as we already saw in the morning class. Okay. Now therefore, there are 2 rigid body like cross-sectional motions. One is the constant vertical translation that is going to be there. So in other words, at some distance x, if I take a cross section, that cross section is going to move up or down by a certain amount, which is what we are referring to v at x. So if that cross section is at a distance x equal to x naught, then we are talking of a v of x naught, which is a fixed value, a certain number, which is a measure of the distance by which that cross section moves upwards. Okay, if it's negative, it's obviously moving downwards. Okay, so there is a constant vertical translation, either upward or downward, of all the cross sectional points. So in other words, when we say there's a vertical translation of the cross section, it's like the cross section is moving almost like it's a rigid body, right? So in other words, every point on that cross section, if I take one point over here, if it's moving by, let's say, 5 centimeters, a point over here is also moving by 5 centimeters. A point here, wherever I choose on the cross section, they're all moving by 5 centimeters, right? So which means that the cross section as a whole is moving like this by 5 centimeters, which is why we say it's a rigid body like displacement. But remember, I'm not saying rigid body displacement, because one cross section here might have moved by 5 centimeters, a cross section here might have moved by 6 centimeters. So in other words, the beam as a whole different points are moving by different amounts. But at a given cross section, all the points, material points on that cross section are moving by the same amount. But at the very adjacent cross section, it could be much larger motion. At the very adjacent cross section this side, it could be a much smaller motion that is happening. Okay? So keep that in mind, that whenever we say rigid body motion, it is not actual rigid body motion, but rigid body like motion, because the cross sections are all connected to each other, and adjacent cross sections can move by different amounts. But a given cross section, the major displacement that is happening is essentially in terms of a rigid body like motion, and that is all that is of significance as far as this course is concerned. But in more advanced beam theory courses, we see that actually the points may not be moving by the same amount even within a cross section. There is a Poisson's effect. For example, if I am pulling this, there is going to be a contraction, and already you know that bending is going to be causing certain compression and tension. So at those locations, there is going to be a shrinking in the other direction wherever there is tension, and wherever there is compression, there is going to be an extension in the other direction. So obviously you can see that the points are moving apart from each other, which is what we call as the in-plane warping, in-plane cross-sectional warping. Similarly, if it's a torsion, we saw some of the examples that you showcased today, like the rectangular cross-section, solid as well as hollow, the elliptical cross-section, all of those are going to do warping. Okay? In other words, warping not only within the plane, but out of the plane. So different points and different locations are going to move out by different amounts, unlike a circular cross section, which is not going to warp at all. So in other words, there's no translation happening there. If at all there is, it's a constant for all points on that beam. So therefore it's not called a warping. Okay, it's only the differential motion which is called warping. So it's essentially, warping is a three-dimensional effect of out of plane or in plane, but it's beyond the scope of this course, so we will not talk about warping here. We are essentially, that's one of the assumptions we are making, plane section remains plane, means that we are not allowing it to warp. Now, constant vertical translation is one of the rigid body like motions. So that's the reason why I have highlighted like. So many people tend to think because it's rigid body, everything about rigid body will apply here. But as I said, two adjacent cross sections can move like two different rigid bodies, and since they are connected, the beam as a whole is not behaving as a rigid body. It's only part of the model which deals with the cross section which is behaving like that. Okay. So the other motion that is there is obviously a linear axial translation of the cross-sectional points. So in other words, a point over here, a point over here, they are all going to translate in such a way, the point on the top over here is going to have a negative x direction motion. So in other words, it's going like that, and a point over here is going to have a positive motion. So essentially, as a cross-section as a whole is going to rotate like a rigid body. Okay. So there's a translation like a rigid body, which is what we are calling as V of x, and there is a rotation that is taking place, which is what we already encountered as theta of x, which is nothing but the derivative of V of x. Okay. So in other words, these two are kind of related in this simple beam theory that we have. These are not two independent motions. One is the translation in the vertical direction is essentially happening, which is what we are calling as V of x, and there is a rotation that is happening which we are calling as theta of x. Okay? But in more advanced beam theories, we will see that these two are independent degrees of freedom. In other words, the theta major part of it, yes, will be V prime of x, that is the first derivative of V, but there can also be a small additional rotation as well, which is not dependent on V, and therefore these two are independent quantities. Again, that is beyond the scope of this course. We will stick only to this fact that these two are related to each other, right? The first results in a constant vertical translation. The second results in a constant rotation about the z-axis. Now, since we have two of these, we need greater than or equal to two constraints in order to plug the entire body's rigid body motion. See, what we are talking of is the rigid body like motions of the cross section there. But now we are saying that if you don't want the entire beam to move like a rigid body, you have to constrain it at least 2 times. For example, if this is a body over here and I just fix one of these points over here, then it's no longer able to translate, but it's still able to rotate, right, about that point. So, but now we are already talking only of 2D deformation, so we are not talking of any possibility possibility of this moving out or in of the into the plane of the screen. So which means that we are only interested in 3 motions, that is 2 translations within the plane, horizontal and vertical, and rotation, right? So now you are looking at 2 constraints to plug the entire rigid body's motion, more than 2 constraints, because you essentially need to make sure that the body as a whole, because this is a free beam if you're considering the entire wing, but now once you put the fuselage over there, you're essentially making it constrained over there, and now you're saying that this is not moving as a full free beam, that fuselage is essentially constraining at middle. So in other words, the constraints need not always be at the ends of the beam. Okay, more often than not, it is at the ends of the beam, but there are problems in which you could have constraints somewhere in between rather than at the ends, or you could have a combination of certain constraints at the ends and certain constraints at the certain intermediate points as well. Okay, so you have to be open to all kinds of possibilities. Right. So one example is a fixed end. So when you have a fixed end, what happens? You are essentially constraining the displacement and the rotation both to be 0, right? On the other hand, if there are if there's a pin, a single pin is not sufficient. If I pin this, if I fix this end, it no longer can move as a rigid body, even if I keep the other end free, right? Because it becomes a cantilever beam. But if I only pin one end and leave the other end as it is, it can rotate as a rigid body in that, even with 2D deformation, right? So that is the reason that if you have one pin, it is not possible. You have to have at least 2 pins. Okay, 2 pins will keep it statically determinate. More than 2 pins will make it statically indeterminate. We'll get there when we reach there. But right now, this is the minimum required, which is why we are saying that greater than or equal to 2 constraints. Okay. So at least 2 constraints on the forces and or moments. Okay. So what's happening in a fixed end? Both the force and the moment are coming from the support, the fixed end support. If it's a pin, only the force is coming from that, the moment is not coming. That's why you need 2 pins. Then you have 2 forces coming from each, one from each of these pins. Okay. Next, let's look at in terms of the constraint forces examples. The reaction force and moment at a fixed end that I already mentioned of a cantilever, and the other case simply supported that we saw in the previous slide, where we have the reaction forces at the 2 ends of the simple supports at the 2 pins. Also, we have 2 global equilibrium equations available for the beam as a whole. Okay. So which is that you have the summation of forces in the vertical direction equal to 0, and the summation of moments about the z-axis, which is coming out of the plane of the screen, that is also equal to 0. From that you have 2 sets of global equations. So you can find the reactions, all the reactions for a statically determinate problem just by using that, which is why it is in fact called statically determinate, because static equilibrium equations are sufficient to solve the problem. So next, let's look at the example of a statically indeterminate problem like this. Okay. So now if the constraints are more than 2, like in this particular case, there are more than 2 constraints that are involved. So then what will happen is that you are unable to find all the reaction forces directly from static equilibrium. Okay. So which means that the bending moment at any given cross section will depend on one or more unknown reactions. For example, in this case, you see that at this end, I don't know the force and the moment. Okay. And at this end, I don't know a force. So there are already 3 quantities. Now I have only 2 equilibrium equations left, because the horizontal is trivial, it's just a 0 equal to 0. I have only a vertical force equilibrium and a moment equilibrium. Okay. And it's a 2D motion, so these are the only 2 things. So I have 2 global equations of equilibrium for the free body diagram of the entire beam, but I have more than 2 unknowns. What are they? There are 3, one force here, one moment here, and one more force over here at this end, right? So which is the vertical force that comes here, the vertical force which comes here, and the moment which comes here. 3 quantities to determine, but only 2 equations, summation Fy equal to 0, summation Mz equal to 0. Okay. So how do we go about that? So you can't use just static equilibrium to solve the problem. that's why we call this as an example of a statically indeterminate problem. That would be the case even if you had a clamp over here. It will be an even more higher degree statical indeterminacy, because now you have two quantities undetermined here, which is force and a moment, and if this end was also fixed, you will have again a force and a moment here. So totally 4 quantities to determine, again only 2 equations, summation Fy equal to 0, summation Mz equal to 0. So 2 quantities will remain unknown. So we have to do the entire derivation using those undetermined quantities, just call them F and M, and then you go on deriving everything F naught and M naught, and finally you will be able to solve once the deformation is also determined. So that's how such a problem is solved. A little more complex, but it's not that it's not solvable. It is regularly solved for many problems. Okay. So additional information about the deformation is required, more over and above the static equilibrium equations. So you need to know how to find that deformation. Okay. So which is what we are getting to over here. Okay. So now that we know we have to find the deformation, now the question is, how do you go about finding that deformation? So we already saw 2 schemes, integration, definite as well as indefinite integral. There are other methods also, like solving the governing equations. We will get to that. But now for a statically indeterminate problem, how do you go about doing this? This is an algorithm. Okay. So now we are in the knowledge that we cannot find all the reactions from equilibrium. Some of them we can solve. 2 we can solve, because we have one equation summation Fy equal to 0, another equation summation Mz equal to 0. From using those 2 equations, we may be able to solve for 2, and the other quantities will be unknowns still, the other reactions. Okay. So we will express those bending moments in terms of those unknown reactions, calling them some F naughts and M naughts, and in terms of them we will get all the bending moment distributions for the entire beam. If necessary, if there are concentrated forces, we will divide it once again into subdomains, and each one of them will get an expression for the bending moment we can write, but it will all be in terms of certain still to be determined quantities, namely the unknown reactions. Okay. Now we want to find the deformation. One way to go about it is to integrate the bending moment expressions that you have got, but now they are in terms of unknown reactions. But integration can still be done because they are not functions of x. So you can still take them out of the integral when you are integrating in any term that they appear, and you can integrate the rest of the terms. So it is still possible, but these F naughts and M naughts, the unknown reactions, will still be floating around in the problem. Okay. Now, how do we find the deformation? So first of all, uncalculated reactions that are there, and then of course in addition you will be introducing more unknowns. Each time you are integrating, you will introduce one integration constant. Those are also not yet determined. Those also are coupled to each other in general and have to be determined at the end along with the reactions. Okay. So this is what are the unknowns. Unknowns are 2 sets of unknowns. One is the uncalculated reactions at the supports, a fixed support or a hinge support, whatever it is, and the forces and moments at that. And the other one is at each time you have integrated, because you want to integrate the bending moment expression in each subdomain twice to get to the displacement. So you're going to get two integration constants each time, as many as there are number of subdomains, right? What are the equations to solve them? You have greater than 2 displacement and or slope boundary conditions. For example, if you have let's say one of the ends is fixed, you know that the displacement and slope at that end equal to 0. If it's 2 hinges are there, then you know that at those 2 hinges you have the displacement equal to 0. So there are at least 2 displacement and or slope boundary conditions that are present in many problems. So that's one set of equations that you can use. The other, even in a statically indeterminate problem, and the other case, the other set of equations is that when you're dividing the beam into subdomains at each concentrated load, whether force or moment, you will end up with interface continuity, C1 continuity, which means that displacement and slope have to match on the left and right side of that interface where the load is acting, concentrated load is acting, and therefore you can solve for the condition for displacement equal to each other on either side and slope equal to each other on either side. From those two, you are getting two equations that you can utilize. And once again, we find that after you incorporate all of these equations, you will see that the number of unknowns is equal to number of all these equations put together, even in statically indeterminate problems, just like what we explained in the simply supported case, which was a statically determinate problem. Okay, now we'll try to include certain complications in the loading, and these are almost a daily experience as far as aerospace structures are concerned, an elliptical kind of a distributed load. But right now, for simplicity, let's just take a cosine distribution of the load. So it varies as some cos of some quantity times x. So that is essentially what this is proportional to, going to 0 at the end, and the maximum value is at the root. And this is a statically determinate problem, which is a cantilever, fixed end and free end. And we want to see what happens. There are no concentrated loads, so I don't need to divide this beam into subdomains. I can solve it at one shot for the entire beam. Right? Now, one of the things that is typically asked in such a question is, what is the tip displacement? If we find an expression for the displacement of the entire beam, V of x, I can just substitute x equal to L at the tip of the beam and get V of L, which is the tip displacement or deflection, right? So one method which you are already familiar with to handle this is integration. And how does that work? First of all, we'll find out the bending moment. How do we go about that? I will cut the beam at some location over here, and then I can see what is the load which is acting, which is the location at which the resultant load is acting, and multiply by that distance from the point of cut in order to get the bending moment at that. So similarly, I can get up to that end. That is one way of doing it, starting from the left end. The other way is, first of all, I'll find the reactions at this point. The force here should be just an integration of Q dx over 0 to L. So that will be the total force which is acting. So that should be the total force at the support. Then I can also find the Q of x dx multiplied by x, which is the moment arm, and then I can integrate that and find the resultant of that. So then it will give me the moment at this particular location. So I can first determine that, and then I can start marching from this end, which is usually a little more complicated for this problem, much easier to march from the right end over here. Okay. So here you find the bending moment. So one way to do it, as I said, is to use the free body diagram of the entire beam. Because there are no concentrated loads, you don't need to have multiple free body diagrams. One free body diagram is enough. You will use that to find the support reactions. Okay. And then you will integrate this Q of x twice, because we saw that earlier I had written on the board in the morning session, we had derived these two equations, that the Q, V and M are related to each other as first derivatives of each other. So if you take the first derivative of V, you will get Q. If you take the second derivative, you will end up with V with the appropriate sign, because of the sign conventions that we showed in the morning. So both of these are negative. In other words, Q minus Q dx is the change in shear force from one end. So in the entire length, if I take just one small infinitesimal length dx, and this remote is that dx, then at this location there is a shear force, this location there is a shear force, but those two are not equal to each other. That change is what we are calling as dV, and that change obviously has to be equal to Q dx, because Q is acting on this, and it's going to be have to be equilibrated in terms of overall forces for the free body diagram of that infinitesimal length element. Therefore, dV has to be equal to minus Q dx, which is where from we are getting the fact that Q is nothing but the first derivative of V. So if you want to find V, since we already know what is the load distribution, we can just integrate this equation. I can get the shear force. V is the notation we will use in the rest of the slides for the shear force, and M is the notation we will use for the bending moments. And so the other thing is, of course, that you have V times dx is going to be the change in bending moment from one end to the other of that infinitesimal length element. On one end it is m, the other end it is m plus dm. So the net result is dm, m minus m plus dm is going to be minus dm, and that is going to be have to be counteracted by your moment arm V times dx. If you're taking the moment about one end, you don't need to take the force at that end, you need to take only the force at the other end, which is your V reaction V, and therefore that is going to be it. Now you might ask, what about the moment which is coming from Q? But that Q is Q multiplied by dx and also multiplied by again dx by 2 or whatever fraction of dx, depending upon the shape of the distribution. It's going to have a dx squared, and when we take the limit as dx goes to 0, that term is going to vanish. Only this term is going to be there as far as the moment equilibrium equation is concerned, and therefore your dm is equal to minus v dx. I bring the dx down here, it becomes the first derivative of m is equal to v minus v, and therefore I can integrate this. Once I integrate, because I know q, I integrate this equation to get v. Once I substitute that over here, I can integrate this equation to get m. So that's how you get to the bending moment, which you need in order to calculate your displacement. How do you calculate the displacement once you have m? You have an expression for m which is valid throughout the length of the beam for this problem, because there are no concentrated loads, and if it's made out of the same material throughout the length, E remains the same. If it is the same geometry, shape and size, then I remains the same. It's actually IZZ, so I remains the same throughout, so that's a constant. So all that remains unknown is your V of x. I take the EI down to the left hand side, m by EI, and integrate it. I've just now determined m of x from this by 2 times integrating q of x. Then I substitute that m over here. Once again I have to integrate 2 times. So totally 4 integrations are involved. Going from q to v is one integration, going from v to m is the second integration, and from going from that m to the theta is one integration, and going from theta to v is one more integration. Totally you have 4 integrations before you end up with v of x, even in a distributed load problem like this. When you do not have any distributed load, this just goes to 0. So the governing differential equation becomes quite easy. It's only that the concentrated loads will be there. You would have divided the problem into subdomains, and each subdomain will have a different expression for m, and then you will have to integrate each one of them and apply continuity conditions between them, that 2 subdomains are attached to each other, which means that they cannot have a jump in displacement. They cannot also have a jump in slope. In other words, it has to be continuous and smooth function, the deformation, and by using all of that you can still determine it. Any questions or doubts on this? Okay. Right. Now let's continue to get ourselves a little more immersed in the differential equation for the beam. Remember that this is the differential equation for the beam. You can also look at it as, this is a second order differential equation, but you can look at it as a 4th order differential equation if you want to write in terms of q of x, because q of x will be the d squared by dx squared of this. So essentially it becomes a d4 by dx squared. If EI is constant, comes out. That's essentially a 4th order differential equation, right? So now that's what we are heading to in this slide, because we have m. Next thing, we are going in the other direction now. So now we have m over here. So we can take the derivative of m, that gives you v in a with the appropriate sign, and then you have one more derivative and you get to q, right? So this is an inverse problem where you're trying to say, if I want a certain deflection pattern, I want a certain v of x in a beam, I know what material I'm using, what cross-sectional geometry I'm using, so I know E and I. So then, can I go from v of x all the way to what load distribution q of x I should apply in order to get that v of x? Yes, that's much more easier problem. No integrations are involved, only differentiations. All that you do is 2 derivatives of v. You end up with a proportional factor for m. Then you take one more derivative, you end up with v with the appropriate sign. Again, you take one more derivative and you end up with the load that you have to apply, the distributed load that you have to apply in order to get that V of x. Okay. So many a times you would have this inverse problem also. So keep in mind you can go in either direction, from V to Q or from Q to V. Once again, goes with what we have been talking about in terms of our 4 sets of variables and the equations that relate between them, 3 of them. What are we going from? The load is your Q of x, okay, at one end of the table. The other end of the table, the deflection, that is V of x. In order to go from one to the other, intermediate, we are using this M and V, so that you go from one stage to another. You go through the kinematics, you go through the constitutive law and the equilibrium equations, or the other way around. Okay, start with the equilibrium equations, then the constitutive law, then the kinematics. So either way, depending upon whether you have a direct problem or an inverse problem. So now if we combine all these 3 equations, instead of a second order derivative, you have a second order differential equation, a first order differential equation, a first order differential equation. If you combine all of them, 2 plus 1 plus 1, you end up with a fourth order differential equation that you have over here. That and in general you can have E and I changing along the length of the beam. The material can change along the beam, the I can change along the beam. So in general, EI of x, EI can be a function of x, E can be a function of x, I can be a function of x, so that the product EI is a function of x. In that case, this is the more appropriate equation to use. Only case where it's a prismatic beam, homogeneous beam, same material throughout and same I throughout, it's possible that E and I change in such a way that EI remains a constant. Then also you can take this out and just becomes d4V by dx4, right? And the other side, of course, is just Q of x. Okay. What happened to the negative signs? There are 2 negative signs, so it becomes positive over here. Okay. Now we look at equilibrium equations. The equilibrium equations that we have over here are which we saw at the end of the previous slide. Now the simple case is, as I said, when we have EI to be a constant throughout the length of the beam, so EI can be taken out and you have a fourth order differentiation of V to get to Q, okay, or the other way around. So now if you look at the slope, you have to get it as dV by dx, that is the notation we have used for it, theta, and then M of x is the second derivative, which is the curvature multiplied by EI, right? Then if you want the shear force, you end up with the negative of the derivative of M, because V is equal to minus dm by dx, as we already showed from equilibrium, moment equilibrium of an infinitesimal element of length. So therefore we can integrate that to get there. That's a cubic differential, in other words a third order differential equation in terms of V. So depending upon which variable you're looking at different orders of the differential equation. At the most you end up with a fourth order differential equation right at the top. Okay. Now we look at, we have already in fact looked at this kind of a summary of that. We have looked at the different kinds of supports we can have for beam, and there are 4 types: fixed, free, hinged on rollers. Okay. These are the 4 kinds of supports that you have at the 4 ends: top left, top right, bottom left, bottom right. And depending upon how you combine these 2, you get different kinds of beam. If you combine fixed and free, you end up with a cantilever. You combine a pinned and pinned on rollers, you end up with a simply supported, and there can be other combinations of these 4 as well. Okay, you can have a free beam floating in space, like something which is let's say fallen out of a satellite, for example. It's a free beam floating in space, and depending upon its own self weight and or any actuators it has, it could have certain load distributions, how it behaves. It will also have certain rigid body modes because it's not fully constrained. Okay, so therefore you have to eliminate the rigid body modes, and then you have to get to the actual deflection modes. So it's a little more complicated problem to solve, but once again tractable. Okay, that's the simplest on one end of the spectrum. The most complicated on the other end of the spectrum is, in other words, in terms of more constraints, is both ends are fixed. Okay, so fixed, then you have many more constraints in terms of the geometry, because u and v are equal to, sorry, v and theta are equal to 0 at both the ends. So that will make it a little more complex in terms of the levels of static indeterminacy, but we already saw how to determine that as well. Okay. So these are the boundary conditions for 2D deformation. This can be extended to 3D deformation as well. Okay. The one example that we already saw for the fixed hinge beam. So we saw that this is a case which results in more number of unknowns than the number of static equilibrium equations, but we saw once we introduced the displacement equation, we were able to solve for that. So the another way of defining a statically indeterminate problem is that the number of Dirichlet boundary conditions are greater than the number of Neumann boundary conditions. Method 2, now so far we have been focusing on integrations, right? So either definite integrals or indefinite integrals. Now another method is to treat this as a boundary value problem. So essentially a differential equation that you have, you want to solve that with associated boundary conditions. You can solve that in many different ways, standard ways that you have learned in your differential equation course. Okay. So what do we need? We need the applied loads and the boundary conditions, right? Now the applied loads, why do we need? Because that's what is going to define your differential equations right hand side. Remember, you had q of x in the right hand side of the equation which involved the second derivative of m. So essentially you are looking at the applied loads defining the right hand side of the governing equation. The left hand side is the same irrespective of which beam you are considering, what boundary conditions you are considering, what supports you are considering, what kind of loads you are considering, doesn't change at all, the left side of the equation. It's only the right side of the equation, and that is 0 whenever you have no distributed loads. If you have only concentrated loads, no right hand side is 0. But the beam breaks into subdomains and you have to solve subdomain problems. But if you have a distributed load, whatever that q of x is, that becomes the right hand side of the equation. That's why applied loads play such an important role in determining the differential equations right hand side. So this is essentially the equation that we are talking about. You see that the left hand side is a standard for all beams. Doesn't matter, doesn't change at all. Okay. Even when you have not a prismatic beam, let's say a tapered beam like what you have typically in wings, where you have a smaller chord at the tip and larger chord at the root, smaller thickness at the tip and larger thickness at the root. In all those cases, you have different material distributions along the length. The problems that we saw in Boeing yesterday in terms of the fin, that where they looked at the core, where it was changing from different stiffness at one location to another stiffness at another location. Nilesh was there, she might remember. So there again you are having a situation where your EI overall changes because of that, right? Now, but whatever that is, the form of this left hand side remains the same for all beam equations, okay, however complex they might be. Now on the right hand side, however, is where it changes depending upon the applied loads, and once we have that in place, now we can solve for the boundary value problem, which involves that differential equation which I just showed you, along with the associated boundary conditions based on the specific choice of supports. That's where the problem changes. The boundary value problem is different for different beams, mainly because of the right hand side of the differential equation, how the loads are applied, and because of the boundary condition. As far as the actual left hand side of the differential equation are concerned, which gives you the general solution, it doesn't matter at all. It's only the particular solution of the differential equation which changes because of the right hand side being different, that is going to work along with different sets of boundary conditions depending upon different support conditions, and then you're going to end up with different solutions. But overall, essentially the boundary value problem involves a fourth order linear ordinary differential equation, and even if your EI are changing along the length, doesn't matter. Even then, because they are specified functions, you need 4 boundary conditions because it's a fourth order equation and it's linear and it's ordinary. So those 4 boundary conditions can be 2 at each end of the beam. So like for example, what we saw in the fixed end, you have the displacement and the slope specified, or a free end you have the force and the moment specified. A hinged end you have the moment specified as 0. you have the displacement specified as 0. So essentially you have whatever the boundary, whatever the support, you will have two boundary conditions associated with it. They might be both Neumann, both Dirichlet, or one Neumann and one Dirichlet, doesn't matter, but essentially two boundary conditions at each end. But since we have a fourth order equation and 4 boundary conditions, it's a well defined problem, the boundary value problem, which can be solved. And even though our focus in this course is on statics, if we can extend this to dynamics, there will be certain things associated with the time as well, there are more terms, but once again a tractable problem, but instead of an ordinary differential equation, you will have a partial differential equation, because there are two independent variables now, which are x and t, the time. Okay, but that's beyond the scope of this course. Now, what are the two boundary conditions at each end? Examples are either the displacement v of x or the force is known at a support. You can't specify both of them. This is very, very important to remember, that if you had specified v at a support, v of x at a support, you cannot specify the f of f also at the same support. They may not be compatible with each other. Okay? If one is specified, the other can be determined from the equations. Same way, either theta or m are known at a given support, so you cannot specify both of them simultaneously at the same support. Of course, you can have theta at one end and m at the other end. That is fine. Okay? That's not an issue. At the same end, you cannot specify either a pair of v and f or a pair of theta and m. Okay. Now, the entire thing we have been talking about, this is just a example of this. Anyway, I'm sharing all the slides so you can look through the details. Here, I just want you to focus on the procedure. That's what is more important. So here we have the same load distribution that we were talking about, cosine load distribution, 0 at the tip and maximum value at the root. So when you have that, q of x is now q naught cosine pi x by 2l. So left hand side, as I said, remains the same for all beam problems, only the right hand side changes, and is non-zero only for the case where there are distributed loads, which you almost always have in the case of aerospace beam applications. Okay. Now, the boundary conditions, again we'll take an example. In this case, it's a cantilever. So one end is fixed, the other end is free. What happens at the fixed end? The displacement equal to 0, v of 0 equal to 0, and the slope also is equal to 0, dv by dx at x equal to 0 is 0, right? Now, what happens at the free end? We have to specify the shear force and bending moment there. That has to be equal to 0, because there are no concentrated forces or moments there. If there are concentrated forces or moments at the tip, I would specify that concentrated force over here and that concentrated moment over here. Okay? But now I'm not applying any concentrated forces at this end, it's a free end. So therefore, these two are 0, and these are expressions that we have derived for the shear force and the bending moment, just that I'm taking its value only at x equal to l, because I'm interested in the support conditions there, and those support conditions are defined to be 0, right? Now, so it's a easy problem to solve. All that you have to do is to integrate cosine function twice, remains a cosine function, just your 2 pi by 2l comes out twice, becomes pi by 2l the whole squared, and then you are essentially dividing it by EI, and once again integrating it twice more. So once you do, this integration, so it goes the other way around, 2L by pi is what you will get squared, and that you end up substituting these boundary conditions. You substitute x equal to 0 and take v and dv by dx equal to 0. Similarly, at x equal to L, you take these two quantities equal to 0. EI cannot be 0, so it's only that d squared v by dx squared and d cube v by dx cube, which will go to 0. So you see that all these four boundary conditions are in terms of v or its derivatives. This is v itself, this is first derivative of v, second derivative of v, third derivative of v. All are going to 0 at different locations, of course. Okay. So when I say, for example, that you cannot have the force and the displacement at the same location, I can't specify the variable and its third derivative simultaneously. That's what I'm essentially saying. Similarly, I cannot specify the slope and the moment to simultaneously at the same location means that I cannot specify the first derivative and the second derivative simultaneously. Okay, just keep that in mind. So once we solve for the entire thing, this is the solution we get after substituting the boundary conditions as well. So we get v of x is equal to this as a function of x, and we can of course plot that v of x versus x by n. Instead of plotting absolute numbers, we can have a non-dimensional way of expressing the displacement by multiplying by a quantity which has the units of 1 by displacement, which depends on just the beam parameters, EI divided by Q naught L power 4. You can see that this is in Newton per meter, this is Newton per meter squared, this is meter per 4, this is also meter per 4. So I and L power 4 will cancel in terms of dimensionality, and this is Newton per meter squared and this is Newton per meter. Therefore, you will have just 1 by meter, and that's what V of x is. So this is a EI, this is a standard way of for many problems where you want to just see in a more qualitative way what is essentially happening from the tip to the root, irrespective of what specific values Q naught, L, E and I might take. You might have a example or a plot which is kind of valid for all of them. Okay, and many a times you'll be interested in the maximum displacement, which happens to be at the tip over here, and how much is it? You can very easily see that you by substituting x equal to L, and all those many of those cosine terms will go to 1 at or sorry 0, pi if it's pi by 2, and once you substitute for all of them and simplify, you see that it's going to be proportional to L power 4, which is understandable. A longer beam will have larger tip displacement. If you have a larger load Q naught, then you will have larger displacement obviously, and EI is what is resisting that. It's the bending stiffness. The larger the bending stiffness, it's going to be lesser deflection, and that larger bending stiffness, as always, you can get from two sources, by either by changing to a material with larger Young's modulus, or by going to a geometry which has a larger second moment of area, which for example could be an I section, which is probably why this I notation is probably more useful rather than people confusing it with inertia, because it's very high for I section, so you call it I, but it's actually not the moment of inertia, it's the second moment of area. Okay, now we are done with reviewing the beam theory, which was already implicit in whatever we did, but just that we are getting into the nitty-gritty details of it to see actually on the ground how problems are solved. Okay, now we are done only with dealing what happened along the length of the beam. We are still not sure what happened at the cross section of the beam itself. Okay, so now we have to look at the cross sectional analysis, because that in fact was the source for solving this problem, because you needed the centroid of the cross section, you needed the I of the cross section as the second moment of area, and sometimes in more complex problems you need what is known as the product of area, etc. So we will see how we can get that, and now we will also combine one more addition to bending, that along with bending, extension is also present. No issues for us, because still linear model, geometrically linear, materially linear, principle of superposition is valid. I can treat this separately, I can treat that separately, then add up the results at the end. Okay, so the other complication we will introduce in this part of the review is that go to more real structures which are used in aerospace, namely thin walled. Okay, so in other words, the walls are thin, so that because the intermediate material anyway doesn't take much of stress, why carry the material there, scoop it out and just have the hollow and outer edges hollow and empty. Okay, so that's your thin walled assumption. Now let's get into looking at once again the coordinate system that we have, same as before, x along the length, y and z in the cross section, intersecting each other at the area centroid. We have still not defined what it is, though you know from other basic math courses. We will just touch upon that in this or the next slides. So the beam, by definition, of course, is a slender structure, in the sense that the cross-sectional dimensions are very small compared to the length. The length, or in other words, the length is much larger compared to the width and the height. Okay, which is what we call as a slender structure. Then the axis along the length, we are calling it as the beam axis, It need not be a straight line, sometimes it could be a curved line as well, but in this course we'll focus only on straight lines, and we'll call that axis as the x-axis, which is what we have indicated here. What we have shown as the beam over here is the deformed condition. What is it was when no loads were applied was parallel to the x-axis. Because there was upward load, there is a positive v of x, and there is a this particular thing is changing this way. In other words, the slope is increasing, the curvature is increasing. So that's essentially what you're looking at there, right? Now the axis along the shorter dimensions, okay, which is what the CS coordinates means, cross-sectional coordinates, okay. So the cross-sectional plane axis, as I already said, are y and z. We have been already dealing with y quite a bit because that's the displacement that we are interested in. The shear force was also along that. The loading q of x and the concentrated loads were also forces were also along that. So you know that y is already there. That was a 2D problem. Once we go to 3D problems, we have to be focusing on z as well. But even in 2D problems, we saw three quantities were about z, namely the moment, the second moment of area, and what was the third one? The curvature. Okay, so all three were about the z-axis. Now beam equations only in terms of the beam coordinate. Okay, so we saw that whether it is EI d squared v by dx squared or whatever, all those differential equations that we looked at, let's say dv by dx is equal to q minus q, d m by dx is equal to minus v. Everything was involving a differentiation with respect to x. All quantities were functions only of x. That's what we are saying, that beam equations are only in terms of beam coordinate, which is why we had differential equations which were ordinary differential equations, or ODEs, right? Now the final beam equations don't depend on y and z. That is at the level that we have so far looked at. But now if the cross-sectional deformations, for example, are of interest to us, then this y and z dependency also has to be accounted for. Let's continue looking at the beam cross-section. Why that y and z are not entering into the problem? There is some homework already that has been done, okay? Not for you, but in terms of what has gone into the picture before we get to that, which is essentially no more homeworks for you, or you already have enough, okay? So coming to this, you're looking at shrinking this finite area into a point, or shrinking this finite thickness into a line, a curve, okay? When you're doing that, you have to put or essentially concentrate all of the properties at that location. So which means that you have to introduce certain definitions, which are the centroid, which is the second moment of area, the first moment of area, the product of area, etc. So which is what we will do now, okay? The cross-sectional effect comes in, one, through the material, what material you have chosen for the beam. So that's the material at that particular cross-section as well. And then the geometry of the cross-section, what shape it has. I have drawn some arbitrary shape. It could be some airfoil which is with or without camber, which means that there is symmetry or asymmetry. But whatever it is, eventually at the end of the day, we should be able to find out what is known as the axial stiffness, which we saw at the end of the previous class, the torsional stiffness and the bending stiffness, all of which we have covered, okay? All of which involve a material property. The first and the last both involve a Young's modulus. The middle one involves a shear modulus. Then you had the one geometric property associated with each of them. In extension or compression, you had area playing a huge role. So we said that size matters, but shape doesn't. But here, both size and shape matter, that your second moment of area and the torsional constant, which happens to be equal to the polar moment of inertia for a circular solid or circular hollow section, but for no other sections are you allowed to call J as polar moment of inertia, or in some sense related to polar moment of inertia. It is a torsional constant to be determined in many different ways. Okay. These cross-sectional properties are found using cross-sectional analysis, okay, which is what we will do in a very, very rudimentary way here. This is a whole research topic by itself, so we will not go into all those details. At the research level, of course, you tend to determine the warping functions in a three-dimensional way and keep looking at more and more advanced techniques to do that, or getting that much more accurately, etc. But we will not focus on that because we are assuming plane section remains plane, which means all warpings are zero. The cross section behaves like a rigid body, but adjacent cross section is a different rigid body. Therefore, the beam as a whole is not a rigid body. The current review topic deals only with extension and bending. We will not deal with torsion right now. Maybe next Thursday's class we will look at torsion as well, but now focusing only on extension and bending. But anyway, this is today's as well as next Thursday's class is only a review. All of this has been covered in the most generic aspect, the state of the art, the way it can be handled. But now we are only trying to look into the black box. It's kind of breaking open the black box and looking at what is inside it, which is what we are doing in these 2 days, this Thursday and next Thursday. Okay, so review topic deals only with extension and bending, not torsion. For any chosen single isotropic material, E is fixed, and so that will be out of the integrations and differentiations and make life simpler for us. Next is the focus is purely on geometric quantities. So in other words, we are dealing only with A and I because we already left torsion out. We are dealing only with extension and bending, and in extension and bending also we said that E is a constant, same material throughout. So there's nothing to worry about E. We'll just take it out of the all the equations. Then you have only A and I left. Okay, that is what we focus on, and one depends only on the size, the other depends both on the size as well as the shape. Okay, so we'll talk about shear and torsion. Not that we are leaving it out for the entire course, just that we want to look at things by slowly building up the complexity level, so that we are not having like some of the curries at our dining hall where multiple vegetables are all put together. So you try to look at one vegetable at a time and look at understanding the taste of each of them or the health opportunities of each of them. So we'll do shear and torsion in the next class, next Thursday. Even for single material, these are more involved. So because once shear and torsion comes, you will see that it's one step of complexity over and above extension and bending. But again, not something to be really worried about. It's something that was within our ability to handle based on the basic math that we know. Okay, first thing about the size, the cross-sectional area. So that's very straightforward, that you are essentially integrating over an area element dA to the limits of y and the limits of z, which can depend on each other depending upon the cross section. For example, if it's a square or rectangular cross section, the limits of y and limits of z will be independent of each other. But if it's, let's say, a circular cross section, for example, the limits of y and z will be dependent on each other, and instead you can work with polar coordinates r and theta, and then it will become simpler. It will be limits will be only in terms of r, not in terms of theta, etc. But essentially the integration is over AC, which is the overall cross-sectional domain, which is the shaded portion of what you see over here, and the units for that, for area, as you very well know, are meter square. So next level of the geometry that we are interested in is not only on the size or quantity, but something to do with the shape as well, and which is where the first moment of inertia, moment of area comes into picture, where we are trying to essentially utilize it to determine the location of O. We don't know O a priori. We don't know the centroid a priori, except for some very simple symmetric cross sections. We know that it's at the intersection of the planes of symmetry if you have two planes of symmetry which are at right angle to each other, or if it's a single plane, a single symmetry like in an symmetric airfoil like NACA 0012, then you essentially say it's at the midplane, but within the midplane where it is, you have to determine. But in a general case, how do you go about determining it? For that, you need this concept of the moment of area from which a centroid can be defined. Otherwise, moment of area doesn't by itself play much of a role for most problems. It will for some shear problems, etc. But that's not out of our consideration today. Okay. For bending and extension, this doesn't play any role except to help us to determine the centroid. So now area centroid. Again, we have to be careful. It's not the mass centroid. Okay, what we call as the CG rather, or CM. Okay. Now coming to the integrals. So all that we are doing is, in the previous slide, we were integrating just dA to get to the area. We are just multiplying it by one moment arm, which is y in this case, because the distance from the z axis. That's why the subscript z on the left hand side. Okay, you're seeing that when you want qz, you are multiplying by y, and when you want qy, you're multiplying by z. Students initially get confused about that, but remember that qz is the moment about the z axis. If you want the moment about the z axis of all points, obviously it's a distance from the z axis, and that is measured by y, not by z, right? Similarly, if you want the qy, it's the moment, first moment about y direction, which means about this axis, which means it's a distance from the y axis, which is measured by z, and which is why you have z in the integrand over there. And very easy again to see that the units are meter cube, because area is meter squared, and either y or z are just meter, so product is meter cube. Okay. So as I said, the main purpose of using the first moment of area in this today's class is just to determine the centroid. How do you determine the centroid? Once q's are known, you just have to divide by the area, because those will be, you will take any arbitrary point to start with as the xy coordinate system to origin, and then from there you want to determine the location of O, and once you do that, you will shift your coordinate system to there, and for the rest of the derivation keep the coordinate system there. Okay. Only when you don't know exact location of O, because absence of planes of symmetry, you have to choose somewhere else to start with, and in terms of that you calculate those two integrals, then divide them by the area, which you got in the previous slide, integral of dA. Once you do that, you end up with y bar and z bar to help you locate O. You would have done probably many problems like this, not only in engineering but in high school as well. It's more of a revision of that. Okay. To put it the other way around, if you know already the location of the CG from any other point, you can get the first moment of area just by multiplying the area by the distance along the y-axis and the z-axis to get qz and qy. So it's not respectively but irrespectively, right? First moments of area are equal to 0, obviously, if the axis passes through the area centroid. Is another way of saying the previous thing. It's more a corollary of that. Okay. Now we get on to the second moments of area, which is of much more consequence as far as bending problems are concerned, and we have already utilized that in a lot of derivations without saying exactly. In fact, we defined it, but we didn't go through the details of it. We saw that in the derivation that happens, a y squared dA term comes out, or integration over the cross-sectional area, and we had called that as IZZ. That's essentially your second moment of area. Similarly, IYY is z squared dA. So you can very easily see in terms of the name how we are extending the first moment of area just multiplied by 1y, y power 1. Here for second moment you are multiplying by y power 2. So the nth moment of area would be y power n dA, if at all it's useful for some purposes. Okay. So now once again that you should remember that there is a interchange. If you want ZZ, you have to multiply by y squared, because y measures the distance from the z-axis. Similarly, this distance from the y-axis measured by z, and therefore the integration is of z squared dA. Okay. And the unit, of course, has gone by one level of length more, because you have a meter squared from here and a meter squared from here. So it's total of meter power 4 that you have over there for the second moments of area. Like moments of area, there is another concept which will be very useful for certain things that we will do. We will see shortly when we have what is known as the 3D deformations of asymmetric beams. So there we will use this concept of the product of area. Okay, you would have heard the term product of inertia when you did the dynamics course, something similar to that, but very different in terms of the physical quantity. Once again, the same unit, but once you're multiplying by y and another time you're multiplying by z. So you're taking a moment about first moment about y and a first moment about z. Total 2 moments are taken, but it's a product moment because it's involving 2 different directions. Okay, so that's IYZ for you. Okay. Also remember that in the case of the moments of inertia definition and the products of inertia, there's also a weighting factor of the mass that is involved, which is not over here, which is why it's only a pure geometric property. It has nothing to do with the material. Okay. Now, the parallel axis theorem, which is also something that you would have read in dynamics for the moments of inertia, that is a similar kind of thing is valid for moments of area as well, just that that weighting function is not there. So all that you do is, if you know certain quantities about the centroid, you can get it about any other point P. Okay, C refers to the centroid, what we had been calling as O earlier, we call it as C over here. So centroid C. So if you know the, for example, the second moment of area about the Z axis, about the centroid, you can get the second moment of area about the same Z axis but about a different point P. Then you, all that you do is just to add area times the distance between those 2 points in the Z direction, which is YPC squared. Okay. So once again, this is something that can be very easily proved. We will not get into the details of that. Similarly, the other direction as well, if you want to get the second moment of area about the y-axis, you have to add the term area times ZPC squared with YZ, because it's a distance from the y-axis that is of interest over here, and therefore that is the Z within the cross section. Okay. Next is the product of inertia, is the product of area that we are talking about. Once again, if you know about the centroid, you can get about any arbitrary point by multiplying the area by each coordinate once, so that overall it's a quadratic once again in the coordinate measures. So it's a y from P to C, Z from P to C is essentially the distance between them. So you're multiplying that by A to get there. Okay. So this is an example of the centroid location and an arbitrary point P location for which these equations are valid. Next, we'll look at most of these things, even though we defined in terms of integrals, many a times you don't actually have to do those integrals because many books will have tables, and you can just pick up for standard shapes like squares, rectangles, triangles, or any polygon, regular polygons, and or circles, ellipses, etc. You will have standard things. So you will take that. Typically, it will be given about the centroid. Sometimes it might be given about corners or edges, etc. But points on the edges, midpoints on the edges. But otherwise, you can always calculate using the parallel axis theorem that we saw on the previous slide, just by adding area times the squares of the distances or the products of the distances from the centroid to that point. Okay, so once you have more complex shapes, obviously the books cannot give you for every shape that is conceivable, right? But many a times you can break up a complex shape into parts. For example, very, very crude way of looking at an airfoil is, let's say, a semicircle and a triangle. Okay, a semicircle joined to a triangle. So you can look at it that way for a first cut analysis. So something like that. So you will have results for the triangle, you will have the results for the semicircle. You will add those two up using all these summations that you see over here. How many of our standard shapes that your actual shape is made out of, you will just add them up to get to your result. And over and above that, sometimes you might have to apply the parallel axis theorem in order to find about a particular axis, and that is usually the centroid of the overall cross section that you might want to get to. So remember that, and not only it has to be about that point, but it also about be about a common axis that it has to be determined. Okay, so just like in the dynamics course, you will not require for the moments of inertia and explicit integration. Here also you do not require that in explicit integration, because you can use standard tables to get those values and then use the parallel axis theorem to move to the centroid of the overall cross section to get to your moments of area, right? And the product of area as well, which is useful in determining the centroid in the first place. Next, as I said in this review, we are looking at the thin-walled assumption as well, apart from combining extension and bending, which is why we need to see certain things which are specific to that. So it's the same quantities that we just talked about for a generic section. Now we want to specialize it for sections which involve thin walls. So in flight vehicle structures, the cross section built up with typically thin parts. So you might have single cells or multiple cells, and these are kind of connected to each other. Some of these cells might be closed cells, the other can be open partly. So you have certain information about each one of those cells, and then these are all joined in a particular way. So you can use continuity equations in order to get to the overall properties, which is what we want to see here. Okay. First of all, the simplest thing you can deal with is area. So you have the areas of each one of those components. You just add up the areas to get the overall area of the cross section. So, and the useful thing when you have thin walls is that the thickness can be factored out as a constant, and especially it's a uniform thickness everywhere, that T even comes out of the equation. Otherwise, it stays in the equation as a function of arc length S. And once you have that, you are essentially multiplying by that. For example, if you want the area of the thin-walled section, all that you have to do is to take an arc length over there. It could be any arbitrary section like this. So, and you can see that the thickness can vary also. You are essentially introducing the mid line between this. So, and then this coordinate is your S, and at any location you have your thickness T of S. And so to find the area of this, as long as your T is very small, you don't need an integration over T. So in other words, if you look at the overall length of this section, and it's much larger compared to the maximum T that you have for that, then you can just directly use a line integral to calculate the area rather than an area integral, which is what this says. Okay, and the integration, of course, is over the contour domain. S is equal to 0 to see that it is going over there, right? Now, sometimes the contour can be made out of parts. For example, here I've drawn a continuously changing function T of S. T of S can be discrete. In certain location it's a constant, then it becomes a different constant, etc. It can go that way. So in which cases you could break it up into subdomains, like what we've been dealing with in the past as well with the beam cross sections. Here we are dealing with along the cross section, along the contour coordinate, the arc length, and then you break it up into, for example, 3 parts, then it just becomes the sum of those 3 parts. So then negligible thickness effect on the moment of areas. So which means that a lot of expressions will just have the thickness taken out, and you would have very easy formula to remember. For example, if you have that J constant that you are struggling with for some of your homework problems, for a thin walled cross section, it just becomes 1/3 of the length times T cubed. So if this length is C, for example, it just becomes 1/3 of C times T cube if it's a constant thickness throughout. Okay, so something like that. So many problems get simplified because of the thin-walled assumption, and this is a reasonably good assumption to make for a lot of problems, especially in aerospace structures, because of the weight considerations. You typically use thin walls, either closed sections or open sections. Okay, so I think we'll take this as well in today's class. We'll look at on one more review topic what we have covered, but we just want to get into some of the subtle aspects of it. Okay, so coupled beam deformation we have looked at in morning session as well as the first half of today's session, afternoon session. We have looked at only 2D deformations. Everything was happening in the plane of this particular screen, right? Now we want to see out of plane motion. So we want to see what happens when it comes out. Not a very difficult thing to do, just a slight extension of all the knowledge that we have built up in the morning as well as in the few minutes before this. We will just try to do that. Okay, and whatever is the new addition, I have put it in a color coding of black over here. whatever we already know, we have in white, so that you know what is exactly the extension that we are trying to do, okay, or generalization that we are trying to do, extrapolation that we are trying to do. Now the beam axis is in the x direction as always, so you see that. And for the beam's general deformation, which is a three-dimensional deformation, you have not only a load applied in the y direction like what you had over here, for example the lift in the case of the wing, but you also have a drag which is in the other direction, right? So which is either out of the plane or into the plane. The thrust is also of course acting in the opposite direction as the drag. Now so that's one change that we are going to do, to include a z load. Next is in terms of the integration over the beam cross section. You already had one shear force which was along the y direction. The load, displacement and the shear force, always remember, are in the same direction, right? So all of them were only in y in whatever we did so far. Now we are saying that it's not only in y but also in z. That's all that we are doing, okay? So that you already had a y shear force, now we will possibly have a z shear force as well. Now we saw three quantities all about the z axis, the moment of area, the bending moment and the curvature. All of them were about the z axis earlier, okay, because we had an I cross j. Now we could have possibly about y as well, okay. So what was only along y now can have a possible z direction. What was only along z can now also have a y direction, because y and z are both cross-sectional coordinates, okay. So we took one cross-sectional coordinate at a time to understand concepts a little more clearly, but in general we will have in both the directions, and which is what we are trying to do. So y deformation and possibly the z deformation as well, okay. So this, instead of v of x, or rather in addition to v of x, we will also have w of x along the z direction, which is coming out of the plane of the board. For a right-handed system, I cross j will come out, k. Now if you have a symmetric cross section, then of course the z deformation only with z loads. So in other words, you have loads in this direction that will affect only the deformation in the z direction. This load in this direction will affect only v of x. But if you have an asymmetric cross section, for example an asymmetric airfoil which is having a non-zero camber, then you will have one affecting the other. So in other words, there might be a load in the y direction, but it's not, its main effect of course will be a deflection in the y direction, which is v of x, but it can also have a deflection w of x, which is in the z direction. So that has to be taken into account, and that's where this quantity that we introduced but we did not use so far will come in handy, namely your product of area IYZ, which was integral of YZ times dA. Remember that we just introduced a couple of slides back. That's going to become crucial over there when you're dealing with cambered airfoils. For example, you have a Z deformation even without Z loads. That is, Y load is causing a Z deformation. Okay. Again, it's all the same, just that your Y and Z are getting interchanged, and sometimes you have to be careful with the signs. So just watch out for that. Once again, you define a neutral axis. This time it's the line with the zero longitudinal strain again, of course. And the idea is that the neutral axis length remains unchanged. And therefore, you're essentially saying that if you take along the entire length of the beam, if you're taking just a small length, this is of course a cross section, let's not confuse. So it's along the entire length, you're taking just a dx over there. Within that, irrespective of what loads you have, what kind of complexities you have in the geometry and or material distribution, you are going to have a constant curvature within that infinitesimal length element dx. And you call that radius of curvature rho, and subtending an angle phi at the center of that curve, if it's thought to be a part of a circle, let's say. And then you're essentially saying that you have to have that difference. So this is what we already did. Remember, to calculate your change in length, we are just taking that whatever is the original length is nothing but the length of the neutral axis, because everything above the neutral axis is getting compressed and everything below the neutral axis is getting extended, because the way the moment is applied is that the it's in a positive direction. So which essentially means that the top portions are having negative strain, longitudinal strain, and the bottom portions are having positive longitudinal strains, and to account for that you essentially see that the negative sign is a fallout of that. So it's the changed length, which is the radius of curvature at a location away from the neutral axis, and multiplied by the same angle subtended, irrespective of where the point is over here. The angle subtended there is the same for the overall thing in terms of the height. I can take any point over there, differs only by y, and that's what this factor takes into account, that the radius has changed by an amount y from the value rho at the neutral axis. So you see that that's the difference, and this is what is your extensional strain. And then you similarly, this is something that we derived already. We are just saying that we can extend that concept to the other direction and say that wherever we had the curvature about the y-axis, we can have a curvature about the z-axis. If we had a curvature about the z-axis, we can have about y-axis. If you are multiplying by y, we are multiplying by z, etc. Of course, accounting for the appropriate sign. So once we do that, we end up with the other curvature kappa z, and you have the stress sigma xx is equal to minus E kappa z times y, and then you have the bending moments. Again, very similar to what we did in the morning. We are taking an infinitesimal area in the cross section, and that area we are multiplying by the stress within that area, which is your sigma xx. So sigma xx times dA gives you the force. The force multiplied by the moment arm y gives you the moment, okay? And that you are integrating over the entire cross-sectional area, and you end up with z, with the moment about z, again with the appropriate direction, because the force is creating moment which is about the in the right-handed system about the negative z direction, and therefore you have a negative sign to account for that. So once you substitute for sigma xx from the top equation, we already have in terms of curvature. So we substitute here, and the curvature and E are constants. If for a homogeneous cross section, E is a constant, and curvature is a one-dimensional quantity anyway. It's a function only of x. So that comes out, and therefore you end up with an integral y squared dA, which is your IZZ. That is what we had already done. Now we have an effect which is an indirect effect as well. That is, there's an my which is caused by the same stress that we have shown over there, that due to the curvature about z, and that's going to cause this. This is because you have an asymmetric cross section. Therefore, your integral of yz dA, which is a second product of area, that is essentially non-zero, and therefore you will have a non-zero contribution for my from kappa z. Okay, usually the direct contribution is kappa z to mz and vice versa, but now we are having a kappa z correlating with my, and this is possible only when this quantity is non-zero, and that's for asymmetric cross sections only. Once again, the neutral axis, etc. Okay, now coming to the strain from the curvature kappa y. So it's just an extension of what we did. We already did for kappa z. We are doing it for kappa y now. The dextral coordinate system, once again, I cross j is equal to k. So the deformation in the negative z direction will be a positive kappa y, and therefore your kappa y will be minus d squared w by dx squared, as you can see from this geometry, and therefore your positive curvature kappa y will result in a positive strain over here at a positive z. Okay, so this is the only difference in terms of the signs that are involved, but everything else remains the same. So your epsilon xx is no longer negative of kappa z times y, it is positive kappa y times z. Okay. Next we invoke the Hooke's law, which is same as for the previous case, just multiplying epsilon xx by E to get your sigma xx. Once again, getting the bending moments, no different from before. You multiply with the stress with the area to get the force, and the force with the moment arm to get the moments. Then you integrate over the entire cross section. Once you do that, and of course your IYZ can in general be non-zero, so therefore you can end up with this expression. Similarly, your my also you end up with this. This is expected. This is on the expected lines, very similar to what we had before, just the direction has changed. But this is coming only because of an asymmetric cross section and the presence of, therefore a presence of the non-zero product of area. Next, we look at the coupled curvature bending moment equation. That is when both are present simultaneously. There is a bending moment about the y-axis, bending moment about the z-axis. This can happen because of the lift distribution and the drag distribution in an aircraft wing, or for that matter a tail. And they are dependent, of course, on the curvatures in the two directions. In other words, the beam is going to, because of the lift, it is getting curved in one way, and because of the drag, it's getting curved in another way. So essentially, there is a curvature which is in both the directions, and it's having bending moments in both the directions as well. And this is what is the matrix which relates those two. It's essentially your bending stiffnesses on the principal diagonal, bending stiffness about the y-axis, bending stiffness about the z-axis. Remember, both axes passing through the centroid, because that's how we have defined it. But it's possible to define it about other points as well by using the parallel axis theorem, and you have to make appropriate changes in the overall derivation. But these results are valid for about the centroid. Now, there's a coupling happening. As you see, it's a symmetric matrix as anticipated. In other words, your correlation between my and kappa z is very similar to the correlation between mz and kappa y. You can invert that matrix, 2 by 2 matrix, to get to your curvatures in terms of the moments, which is again quite handy many a times. Okay. Now, again, the methodology is very similar. First, using integration, either definite or indefinite, and then using the solution of a boundary value problem, solving the differential equations along with the boundary conditions. Let's first look at the integration approach. You're essentially looking at first determining the bending moment distribution using a free body diagram. If there are no concentrated forces and moments in either direction y and z, then it's a single expression for the bending moment throughout the length of the beam, as we have already seen, and that's going to be done with just a single free body diagram. If you have concentrated forces and moments, you divide the beam into subdomains at each location of the concentrated loads, and then you end up with different bending moment expressions for each of them, and you then solve all of them and connect each other by using the continuity of displacement and slope. Now we use the equation from the last slide to find the two curvatures. At the end of the last slide, remember, we had the curvatures in terms of the moments for a generic case where asymmetry was allowed, and then all we have to do is to integrate the curvature in order to find the slope and the displacement, because the first integration of the curvature will give you the slope, and the next integration will give you the displacement. Of course, you have to apply the appropriate boundary conditions, which are anyway available at the ends of the beam as well as at the interfaces where the continuity condition is there for the displacement and the slope. Finally, we look at the stresses from the deformation. We can also get it from the bending moments. Okay, two ways we can approach towards the stresses. Whether you start from the bending moment and get to it, or you start from the deformation and get to it. Okay, let's look at the deformation first. So you have the stress is defined in terms of a deformation parameter, namely the curvature kappa z, right? And you had in another case where you had load curvature only in the other direction, this is the sigma. But both these stresses, remember, are normal stresses and normal stresses in the x-axis. Obviously, since we have a linear model, geometrically linear, materially linear, principle of superposition is valid, and therefore we can add these two up to get to the actual value. Okay, so that's what we do now. Your total sigma xx is going to have contributions both from curvature about z and curvature about y because of bending moments about both those directions. But we are not touching upon bending moment there. We can go directly from deformation there. We will look at going from bending moment after that. Okay. Now we can substitute for the curvatures in terms of the displacement fields as the second derivative for both the z direction as well as the y direction. Once we do that, we end up with this expression for sigma xx purely in terms of V and W, the deformations along the Y and Z directions respectively. So if you know V and W, this is what your sigma xx is going to be, okay? So of course we have to know V and W as a function of x so that we can differentiate it not just once but twice in order to get the two curvatures, and then multiply it appropriately by minus Ey and minus Ez and add them up to get the total stress. Finally, as I said, there's an alternate way to get to the stress if you already know the bending moments, okay? So from the bending moments, all that you do is you have the curvature by multiplying by that matrix which related the curvature and the bending moments. Remember the bending stiffness matrix, and therefore you can just invert that matrix, multiply it by the bending moments, then you get the curvature. So from the curvature, because this expression is there, so you can just directly go from that. So there are two kinds of problems. You want a certain level of deformations, then you can use this equation to see what the stresses will be and whether the maximum is within the allowable limits for that particular material. Or you can, if you know what is the loading situation already, from the loading situation you can calculate using free body diagrams the bending moments, and from there you can end up getting stresses once again and see whether they are once again within the overall limits. Okay, so I think with this we'll probably stop today's class, and okay, I'll just go for one more slide, yeah. So it will be a proper stop. So another aspect that we have to note is what are known as the loading plane and the bending plane, because even if you have a QY, that is a distributed load in the Y direction, and a QZ, you can always find a resultant of those in an appropriate direction, okay? So therefore that becomes the loading plane. Even when you have in two perpendicular directions the load distributions, you can always find the resultant of them, and that becomes your loading plane. And there could be a bending plane which may or may not coincide with the loading plane. That is also important to remember. That's because of asymmetries in the cross sections. That's essentially what we want to touch upon here. So when you have IYZ equal to 0, therefore EIYZ also is not equal to 0. We have off diagonal terms in that 2 by 2 matrix which connected the moments with the curvature. So which means a moment in one direction can cause a curvature in the other direction as well. So the bending plane therefore differs from the loading plane. So in other words, you have a QX, you have a QY, and the resultant of them is the loading plane, but the bending may not happen in that plane, it might happen in a different plane, okay? So that's essentially what we are trying to cover in this particular slide, and again well within the reach of whatever we have done so far in the course, because the 2D loads here are causing 3D bending because the load is within a plane, the resultant plane, but it's ending up in bending in a totally different direction. Essentially you're talking of a 3D bending, and therefore the loading plane implies internal forces and moments, because that's how you calculate, remember, the so-called shear forces and bending moments. For example, if it's a Y loading, then you have a Y shear force and a Z bending moment. We've been talking about this throughout the morning session. And the bending plane, on the other hand, will be about the deformation, strains, and the stresses, because all of that is connected to the bending moments, and that's how you end up with, okay? So you see that already you have Y loading, you have a Z bending moment, and that's what is happening over there. Okay, maximum normal stress, of course, always is at the point which is farthest from the neutral axis, because at the neutral axis there's no longitudinal strain, there is no longitudinal stress. As you go farther and farther away from it, it's proportional to that distance, and therefore the farthest that you can get to based on the geometry of the cross section is where the largest strain, that is axial strain, that is, and the largest axial stress, which is essentially coming from the bending, is going to be there, and that's of course on perpendicular to the bending plane, okay? So yeah, next. Yeah, I think the next Thursday we'll be looking at a few energy methods. We already remember when we introduced the assumptions, we talked about the existence of strain energy, etc. So we will see how to use some of those energy concepts in order to solve the same problems, but in different ways. We already saw the integration method through definite and indefinite integrals. We saw the the governing differential equation of boundary value problem method. We will see some methods using the energy next class. So it's the same problems, we get to the same solutions, but we take a different process, a different procedure. Sometimes this is more convenient and more informative than the other. So it's important for us to review this as well. Thank you.